Hello and welcome. In my last video I shared with you guys that huge pile of hardware which I got from Stibor, a longtime viewer of my channel. He generously donated some really rare and exciting hardware pieces, and in the future I am going to take the parts one by one and introduce or repair some of them in my videos. And I am going to take a closer look at this really exciting 286 mainboard today. As I already said in my last video, this mainboard has an AMD 286 CPU with 12 MHz and an absolutely whopping amount of memory on board. 4 MB as SIM memory modules plus 1 MB of onboard soldered memory, making 5 MB of total memory. An unbelievable number for a mainboard of that time, which almost nobody could afford back then. What else can we find here? The two BIOS ROMs are here, and on the left there are some 16-bit ISO slots, but as you see on one slot the second part is desoldered and a little bit longer. This board already has a lot of RAM, but such longer slots were used for memory expansion cards to get even more RAM onto the system. Such cards were usually very long, with a lot of dip sockets for the memory ICs. What else? A useful feature on this board, a Super I/O controller with a floppy and IDE controller, as well as serial and parallel ports. Back then, usually such controllers were on a dedicated ISO card. Such an on-board controller was an absolutely unusual feature for a board of this age. And apropos age, how old is it actually? Here we see Siemens 87, but this is not a date code, more a copyright message. The Western Digital floppy controller chip here also says 87. This chip says 89 in the date code. This one 89 as well. That one too. So I would say that this mainboard was made around 1989, maybe 1990. Okay, as I said, this mainboard suffered some damage from a leaky battery. And as far as I see, someone already scratched the oxide of the traces a little bit. But the damage doesn't look to be too widespread. I will have to remove some parts, clean everything and see if some traces are broken. I usually don't suggest to start the board before the battery damage was cleaned completely, since current can amplify the chemical reaction and already damaged traces can be damaged even further. But here, someone already cleaned the damaged area and looks like the battery electrolyte was also already neutralized. So let's give it a short try. First of all, I will remove the memory to reduce possible error sources. And since I will wash the board afterwards, I'll need to remove the memory anyway. I really don't like this type of SIM sockets. The memory modules are hard to pull out of them and the old and brittle plastic latches are snapping off really easily. If possible, I always replace these slots by something more steady. A brief test for short on the power rails. 5 volts and minus 5 volts look good. This is ground. Minus 12 volts and 12 volts seem to have no short as well. Very good. Let's connect the AT power cable. Never forget, black to black and all of them in the middle. I will also add a post analyzer card to see if the board is actually alive. And we are ready for the first try. And the board seems to be totally dead. No numbers are running on the post analyzer at all. At least when I turn on the system, the reset LED lights up shortly and goes off again. That means that at least the reset circuitry is kind of alive and the CPU should start the execution. Anyway, let's remove the BIOS chips and the CPU from the sockets. I'm going to wash the board later and it is not absolutely necessary, and I'm often too lazy to remove the ICs from the sockets, but since I have to look into the sockets and clean them as well to exclude any problems with contacts, it's worth to remove the ICs this time. As I already said, luckily the damaged area is not very large, so I will have to remove only some parts around the keyboard connector. On the back side, the mainboard looks as good as new, very nice. A small desoldering note: always add a little bit of fresh solder to the old joints. This simplifies the desoldering process significantly. If the pins don't want to come out by themselves, don't pull on the parts, or you could rip off the pads from the board. Instead, wiggle with a pair of tweezers a little bit on each leg to loosen them gently. Afterwards, you should be able to easily remove the parts from the PCB. So, I removed all the parts which were in the damaged area, and, well, under the keyboard connector it still looks really bad. A lot of corrosion and probably broken traces as well. And under the ICs everything looks quite good actually. I don't see any damage there so far. Still, it is always worth it to remove surrounding ICs, since the worst damage can hide underneath, like under the keyboard connector in this case. Those parts do still look quite good though, so I'll not touch them to avoid unneeded stress for the PCB. So it's time to neutralize the residues of the battery electrolyte using some acid. If you don't know why I'm doing this, I made a video about it some time ago. Please feel free to take a look. However, I'm always getting some questions on this topic. For example, which acid I'm taking exactly. This is a normal white vinegar, which you can buy in any supermarket. This one is highly concentrated at 24.9%. and is a bit too aggressive, so I usually mix it at about 50% with water to get the concentration down to about 10 to 15%. This works really good, and I'm usually using this solution. However, it smells very unpleasant, so there are alternatives. And I got some questions indeed, which other acid can be taken for this procedure. And the answer is simple: you can take any weak acid solution you have at hand. It just shouldn't be too aggressive and attack the copper traces. And for example, today I am going to take a pure lemon juice, of course without sugar. This works just as fine. It is not too aggressive and smells nicely of lemons instead of vinegar. After 10 minutes you already can see that it dissolves most of the oxidation, and what you can't see is that it neutralizes the battery electrolyte residues, stopping it from further reaction. Now, what I have to do is to scrub it a little bit with a toothbrush. And after some scrubbing, the mainboard has to be washed to get all the dirt, dust and the residues of the chemical reactions from the board. And this is another common question which I get: how to wash the boards properly? As I already said, I often don't even bother to remove the socketed ICs. In this case, I removed most of them, but I didn't remove the memory parity chips from the sockets, for example. You should always remove the batteries, however, everything else doesn't matter. So, what do you need to wash such hardware? Well, you will need the hardware, the soap, a brush, it should be quite soft to avoid any damage on the board, and water. That's all the secret. First you have to use the brush to get rid of the most dirt, then add some soap and use the brush again to wash the PCB properly, especially in the place where you used the acid. Many people are afraid of even saying the words water and electronic parts in one sentence, but this fear is not really justified. Water doesn't kill the electronics on its own. However, salt in the water are kind of what you have to think about. If the water is distilled or contains no salt, in other words, you can easily wash all your electronics with it, no problem. But if you use the normal tap water, there are salts in it, and when water evaporates, you see these typical lime stains left behind. This is salt, and this is what can be dangerous, but is usually not a big deal. You just have to dry the hardware properly. But first, let's leave the board soaking in the water for 10 minutes or so. Now the board has to be washed thoroughly with clean water to get all the soap off the board. Take your time and use the brush again to wash all the rests, dirt and soap away. And again, don't be afraid, also don't forget to wash the backside. Once you are done with washing, put the board upright on the edge like this, and leave the board for some minutes to let the water drip off the PCB as much as possible. The less water remains on the board, the less probably you will get the lime stains on it. Pay attention to have the slot vertically like this, so the water can run out of them. If you are unsure, you can use a can of compressed air to blow most of the water from the board and from under the ICs and slots. I usually don't bother. After another 15 minutes or so, I put the board again in such an upright position onto a slightly warm radiator in a dry, warm room and leave it there for another 24 hours to get it really dry. If you are in a hurry, probably even 12 hours would be enough, but to be on the safe side, just take your time. So, about 20 hours passed, and the mainboard seems to be completely dry. This is how the corroded area looks like. Now the rests of the corrosion has to be polished away from the PCB. Therefore, I'm using such green hard rubber tips for the Dremel. You can buy such a set of tips from China for about 10 euros, including shipping and taxes. You just have to set the Dremel to low speed and gently go over the traces with a tip. Don't apply any pressure. Take your time and be patient, or you will polish away the copper in a blink of an eye. Polish only as much as needed, but remove all the oxide until you see the clean and shiny copper. And clean everything with some alcohol afterwards. That is important for the next step. The problem now is that the oxide was actually a copper which was eaten away by the electrolyte and turned it into salt. Now where it is gone, the traces are a lot thinner and weaker. They are not in spec anymore to transfer the current which they were originally designed for. If I would try to use the board now, I would simply risk to burn the traces. Therefore I have to tin them again to regain some thickness. And therefore I put some flux all over the place, add a drop of solder to the tip of my soldering iron and go over all polished and exposed traces. Add some more solder when needed, but don't add too much solder at a time, or you will breach the traces, so pay attention to that, but also don't be too afraid. This procedure is really easy. Thanks to the flux, the solder will tend to flow into the direction of the exposed copper automatically. For me, this is always a magical and very satisfying moment. After everything is tinned and all the traces are reinforced, use again some alcohol to clean the PCB. Also double check now that none of the traces got shorted. If you put too much solder somewhere, use again some flux and maybe a solder wick to remove excessive solder. After cleaning, it's time to check for broken traces. By such a massive damage, there are usually some, and they have to be fixed again. But in this case, there are magically no issues, and I can measure continuity on every trace. Unbelievable, but true. All the removed parts seem to be not damaged, and the values are alright, so I can solder everything back in place. I will not put the keyboard connector yet, since it is not necessary for the test and it could be in the way should I need to follow the traces underneath. I will add some dioxide to all the sockets, clean them and insert the ICs. In case of the CPU, think of orientation. It has no protective key, but in the socket there is such an arrow, or triangle if you want, that must be aligned with this dot on the CPU. It is also important to remember which BIOS IC goes into which socket. If you are interested, I can make a short video about why there are some mainboards with 2 BIOS ICs and some with only 1. But for now, it's just important to know that this one goes into the socket U9 as it is written on the sticker. The other one goes into U14. So once again, the post analyzer, the power cable, and let's turn on. Nope, still the same error. The board is still dead and the fixed corrosion damage didn't change anything so far. Still, that was absolutely necessary, and now it is also not dangerous to let the system run for a bit longer. What can we do to analyze this issue? Well, I'd like to measure if there is some activity on the address lines. That would give us a hint that if the CPU is working at all. Therefore, I will use such a prototyping board which I designed some time ago. I will put the link into the description where you can download the KiCad project. I use this board to design and test my prototypes, and if you find this interesting as well, feel free to produce some of these boards for you as well. As all of my projects, this one is also open source. So the board can be plugged into the ISO slot, and now using the oscilloscope we can measure some signals on the address lines. Thanks to the notation on the prototyping board, I always exactly know which signal I am measuring. Let's try A0. And there is something. Now A1. Yeah, definitely there is proper square wave. So the CPU is definitely alive, that's a good sign. All the address lines seem to be okay. Let's see what's on the oscillator pin. And we have 14.3 MHz, that's fine. And the ISO bus clock is at 6 MHz, interesting. It's half the speed of the CPU. Actually, this clock can be up to 8 MHz, so upgrading the CPU to 16 MHz without overclocking the ISO bus would may be a nice option for this board later. Okay, before I dive deeper, let's remove the BIOS ROMs once again and try to read them with the TL8662+. I didn't find this board in the Ultimate Hardware database, so I will have to dump the BIOS ROMs anyway. The ICs are NMC27C256BQ. The TL8662+ software knows either B or Q, so let's go with B. Reading the ROM seems to work, but when talking about such old ICs, my suggestion is to try to read it a couple of times in a row. This seems to work okay. So, I saved the first ROM into a file and made the same procedure for the second IC. I read the content and saved it into a file, and then I clicked a couple of times on the read button and look what happened. Ah, you see this? Reading the IC has failed and the operation hangs now. This didn't happen with the first IC, but I will take 2 new old EPROMs and copy the content there onto. So the replacement ICs are ready. Let's test them. 0 means even and 1 means odd. I got that reading problem only with 1 EPROM, but I will replace both of them for now. This board seems to be very rare and I didn't find any BIOS images online for this model. I could use another BIOS from a similar board, but I prefer to go with the original now, just to avoid ghost hunting due to some BIOS incompatibility in the future. That's why these EPROMs are a simple copy of the ROMs which I pulled out of these sockets. So everything is already connected. Let's turn on and see if we see some numbers on the post analyzer. And yay, something is happening. So the mainboard is back to life at some extent. Seems like at least one of the original ROMs could be bad indeed. Luckily, I still could read both of them and back up the BIOS, since it seems to be hard to find it for this mainboard. The question is, how could that happen? Well, it's hard to tell now, but my theory is some kind of short circuit, or some kind of current peak. Look at those three blue decoupling caps. Another one is here, for example, and another one of them is here, here, and here. Interesting is that they are all blue, however, those two guys are red. All other caps on this board are blue except those two. My guess is that there was a short on this board once in the past, and someone replaced these two caps. These are tantalum caps, and they tend to short sometimes, and maybe they produce some current peak which slightly damaged the EEPROMs. But this is just a vague theory, and is maybe completely wrong. Whatever happened to the EEPROMs, the board seems to be alive now, and for further tests I will need a keyboard, so now the keyboard connector can be finally soldered in place. So, the next try. Now we can connect the keyboard, a VGA graphics card, which I currently have at hand. It is an OTI 077, but that doesn't matter now. The important thing is to see a video signal at all. And furthermore, I will add a compact flash to IDE adapter with a compact flash card as a hard disk replacement. Luckily, this mainboard has all the I/O ports directly on board. As I already said, very unusual for a 286 board of that time. Everybody who watched my channel regularly will recognize the compact flash card, where I have DOS 6.22 pre-installed with all the required tools, drivers, and even some games. So everything is in place. Oh, one important thing is the PC speaker, so we can hear if there are any post-error beeps. That can help a lot. Now I think everything is ready for the next test. Let's give it a try. And we have a signal. Jaton Super 286 System 2. And we get some checksum errors, which are definitely true, since we have no battery attached and all the BIOS settings were reset. And there is a beep. Strike F1 key to continue, F2 to run setup. We want to get into setup, so F2. Here we have all the errors related to the missing battery. That's okay. And we are in BIOS. Let's do some settings. I have no floppy attached. Okay, I played with the hard drive type IDs and looks like we can use type 48 to set up custom drive and not 47 like it is usually. Well, that doesn't matter. The compact flash card's geometry is 987 cylinders, 16 heads. Precompensation and landing zone shouldn't make any difference, and 63 sectors. That makes 485 megabytes of total size. That looks right to me. What else? I can press page up. And here I can see all the shadowed memory and other tweaking. I will set BIOS and video ROM directly to shadow. That should give some performance boost. If you don't know what is shadowing, watch my video about XT IDE performance, which I made a while ago. Everything else can be left unchanged for now. Let's reboot. The system hangs and refuses to boot from the compact flash card. I can see that the LED on the compact flash to IDE adapter is lit up all the time. Means that the mainboard is trying to access the compact flash card all the time, but somehow that doesn't work. Well, at least we have some activity on the IDE port. That is a good sign. Unfortunately, the board doesn't show an error message anymore, so I can't even enter the BIOS. Let's remove the compact flash card from the slot and restart once again. Now I get hard disk controller failure and I can enter the BIOS once again. Let's see, type 48, 987, 1663. All the values seem to be right. That is unfortunate. So, couple of minutes later, I tried to plug the compact flash cards in and out and also tried to use the type 49 instead of 48 like before, but that didn't make any difference as expected. So, let's try something completely different. First of all, I will set the hard drive to not installed. Now the compact flash card can be inserted back into the slot. Unfortunately, I still can only enter the BIOS if the compact flash card is not installed. And now I would like to reference my series of videos about XT IDE once again. So if what I am doing now looks for you as a magic, please feel free to take a look at that series. And now I will take this network adapter with pre-installed XT IDE BIOS ROM, and hopefully this will help to get the compact flash card in this machine up and running. It was very important to set the hard disk to not installed, so the XT IDE can take over the detection completely. And would you look at that, XT IDE found the compact flash card indeed, so the onboard IDE controller is probably alright. Well, HiMemCs complains about insufficient memory. That's right, we have only 1 MB from which we took some for the shadow. Let's start the check it and see what it says. A 286 with only 640K of base memory. That's not much indeed. And if I try to start Commander Key in game, it complains about insufficient memory too. Well, that is possible to reconfigure and optimize the memory layout to get Commander Key running over with 1 MB of memory. But as you remember, on top of the 1 MB onboard memory, this mainboard supports additional SIM memory. I have here 4 times 1 MB memory modules, which were previously in this board as I got it. So let's push them into the slots and see where we get. Unfortunately, the slots in this board are really bad and I will probably exchange them in the future, but for now, let's just hope that they work. And yay, it counts up to 4 MB of extended memory. The BIOS complains about invalid configuration. And indeed, it detected that the amount of memory has changed. There we see memory 640K and extended memory 4 MB. Actually, the board has 1 MB memory on board, but 384 kilobytes are reserved and not shown here. One more thing I would like to do. I will enable shadowing for the XT IDE BIOS at D8000 address. This should drastically improve the hard drive I/O performance. And as you see, the system boots and HiMemCs doesn't complain anymore about insufficient memory. Let's see what memtool says. Yes, now we have 628 kilobytes of free conventional memory. That should be enough to run any real mode DOS game you want. Check It seems to be happy as well and reports 4 MB of extended memory. And finally, let's see a game running on this great piece of hardware. A time-correct example would be Commander Keen, and now it should have more than enough memory to run. And it does. I'm so happy to have this super nice and rare 286 board up and running again. The corrosion looked fortunately worse than it was, and none of the traces were completely damaged. A little bit of polish and tinning did the trick. However, you hopefully saw once again how important it is to look under every part. The corrosion under the keyboard connector was really bad and would continue to damage the traces if remained undiscovered. Also, never forget that XT IDE BIOS is a great helper if you want to see if an IDE controller is working at all. Many old BIOS versions seem to have problems with more modern drives or compact flash cards, and such a network card with additional ROM can do some magic. Off camera, I also tested the original EEPROMs once again, and the odd one in the socket U14 seems to fail indeed. The mainboard didn't boot reliably if I used that. Luckily, I could still read that one in my programmer. So, what left to say for today? This is a very nice board, and it can not only be used in a nice retro build, but also heavily upgraded. The FPU socket is still empty, as you can see. The CPU is a 12 MHz one, and luckily it is socketed, so it should be possible to upgrade it to something beefier. Therefore, I'd also need to replace the quartz oscillator, but all that is a topic for another day. And today, I hope you enjoyed this repair, and maybe you could take something with you as well. And even if it was just a little fun. Just as always, please leave your feedback below, likes, dislikes, whatever you feel is right for you. And if you like to watch such repairs, please keep an eye on the channel, since I'm going to make more of such videos in the near future, and we'll take a look at the other mainboards which were lately donated to my channel. And for now, I say thank you and goodbye.